Many people think they know how to write C++. They've written classes. They've written functions. They've written templates. They've even worked on some serious projects. But there's one question that most people have never really thought about. When you write a line of C++ code, what is the computer actually doing? Take this program on the screen, just 7 lines of code. Looks simple enough, but let me ask you a few questions. Can the CPU understand include? Does the operating system know what a class is? Is there really a variable called x living inside the memory? When the screen finally displays the number 30, what exactly happened in between? The truth is, the computer doesn't understand C++ at all. It doesn't understand any high-level language. It only understands 2 things, 0 and 1. So today, let's take a look at how C++ really works. First, you need to understand one thing. The C++ code you write is never meant to be read by the CPU. Many beginners assume that when this assignment statement executes, the CPU is executing an instruction that says, define an integer variable called x. That's not actually the case. If you're curious, go ahead and look through the CPU instruction set manual. Page by page, you will never find the word int. You won't find class. You won't find template. You won't find namespace. These concepts were all created by programmers for one purpose, to make it easier for humans to write programs. The thing that truly understands these concepts is the compiler. The compiler is the one that actually reads your code. When you write this statement, the compiler translates it into assembly instructions and then further converts it into machine code, a string of binary numbers. The CPU executes that machine code. So fundamentally, C++ is not the CPU's language. C++ is the language of communication between the programmer and the compiler. The compiler is the real translator. Now let's talk about variables. Many tutorials like to draw a variable as a box with a number inside it. This illustration is easy to understand, but it's not real, because real memory isn't like that at all. Real memory is more like an infinitely long street. Every house number on that street is a memory address. Behind each house number lives 1 byte of data. Take that same line of code. What really happens is this. The compiler says to the operating system, I need 4 bytes to store an integer. The operating system checks its room availability list and hands the compiler an address. Then the compiler stores the number 10 there. Then the compiler makes a note in its little notebook. The symbol X corresponds to address 0x1000. So after compilation, in the final executable file, there is no symbol X. The name X is erased during compilation. In the final running program, there are only addresses. The CPU doesn't know anyone named X. The CPU only knows to fetch data from some address and put it into a register. What about functions? Many people see this line of code and picture the CPU executing a functional module called add. Give it 2 numbers, it computes and returns the result. Is that understanding correct? Yes, but only at the functional level. At the lowest level, the CPU has no idea what a function is. In the CPU's world, a function call is essentially just a jump. For example, the instruction call add doesn't mean execute a function. It means remember the current position, jump to another address, execute the code there, and then jump back when done. Think of it like this. You're reading a book. You turn to page 100 and see a footnote. For a detailed discussion of this topic, please turn to page 200. So you remember your place on page 100, flip to page 200, read it, and then flip back to page 100. That's a function call. There's nothing more complicated to it. A function, in essence, is just a piece of machine code that can be jumped to and executed repeatedly. Now comes the thing many C++ programmers are most familiar with, objects. Many people hear the term object-oriented programming and think it sounds very advanced. Create a person object. It sounds like you're bringing something real into existence. But in memory, it might look just like this. That's right, just 4 bytes. An object, in essence, is just data arranged according to certain rules. Member variables are just pieces of data at different offsets within the object. What about member functions? Many people think member functions belong to the object and are stored inside it. Think about it. If every object stored its own copy of every member function's code, how much memory would that waste? So member functions typically store only 1 copy of the machine code shared by all objects. When you call a member function using an object variable, the compiler secretly transforms it into something like this. In other words, a member function is really just an ordinary function that receives 1 extra parameter. That parameter is the famous this pointer. It tells the function this is the object you're operating on right now. So objects are just data, and member functions are just ordinary functions with an extra pointer parameter pointing to that data. Let's dig 1 layer deeper. C++ has virtual functions. It has polymorphism. A base class pointer pointing to a derived class object calls a virtual function, and the derived class version executes. This dynamic binding sounds very smart. But underneath, it uses a very straightforward mechanism. Every object that contains virtual functions has a hidden pointer at its very beginning, called the virtual table pointer, VPTR. This pointer points to a table, the virtual function table, vtable. The table stores, in order, the addresses of all the virtual functions. So what we call dynamic binding is, at the lowest level, just a pointer dereference followed by a jump. That's it. Nothing more. So the cost of virtual functions is one extra pointer lookup, one extra indirect jump, and one extra pointer's worth of memory space in each object. That's the real cost of polymorphism. Templates might be the most confusing feature in C++. Many people see templates and think they're a runtime, type-adaptive, generic mechanism. But actually, templates have nothing to do with runtime. Templates are compile-time code generators. For example, when you call this template function, the compiler does something very straightforward. It generates two separate pieces of code effectively. The compiler writes two overloaded functions for you. So the essence of templates is a code template that gets copy-pasted at compile time with type parameters substituted, generating concrete code. Alright, so far we've put all the pieces together. From the moment you finish writing your code to the moment the result appears on screen, the complete pipeline looks like this. Compilation phase. What the compiler does is take the C++ code you can understand, turn it into assembly code you can barely read, and then into machine code that's completely unreadable. During this process, class is gone, vector is gone, template is gone, lambda is gone, namespace is gone. All that's left is machine instructions. Linking phase. The compiler compiles each C++ file individually into an object file. Object files contain many placeholders. For example, in main file you called standard cout, but the compiler doesn't know the actual address of standard cout. It's in another file or in a static library. The linker's job is to fill in these placeholders. It merges all the object files together, resolves all external references, and generates a complete, self-contained executable file. Loading phase. You double-click the program, and the operating system's loader takes over. It creates a new process, note, a process, not a thread, and allocates an independent virtual address space. It loads the code segment and data segment of the executable into this memory. It sets up the stack for function calls and local variables, and the heap for dynamic memory allocation. Finally, it points the CPUS instruction pointer to the program's entry point, the start address of the main function. Execution phase. Now, the CPU starts doing its work. It enters an endless loop, fetch, decode, execute, write back, then repeat, billions of times per second until the program ends. Throughout the entire process, the CPU has never seen class, vector, or template. What sets C++ apart from many other languages is this: it doesn't hide the low-level details completely. This is something I really appreciate about it. It always leaves you a window. You can see memory through pointers. You can see addresses through references. You can see the implementation of polymorphism through virtual functions. You can see compile-time code generation through templates. Through C++ code, you can understand how a computer actually works.